This is very nice, and thank you for the introduction. But the most important thing to know about me is that I have 12 grandchildren and 4 children and 1 wife. So now you know what's really important. Now let's go to the lecture. And in the next hour, I will describe to you something about quasi-periodic materials in a way that each and everybody of you will understand. Even if you have students of law, you will understand my talk. Okay, so in order to understand what was happening, let me take you to the mid-80s. And in the mid-80s, there were 3 surprising discoveries on the structure of matter and its properties. They came year after year, and all 3 of them received the Nobel Prize in later years. First in order was the discovery of quasi-periodic material, and the names on that is my name, Ilan Blech, Denis Gratias, and John Kahn. I will tell you a little bit about these people later on. Next came the discovery of fullerenes by Harry Kroto and his colleagues. This is 1985. And the next one was the discovery of high-temperature superconductivity, 1986. Now, when high-temperature superconductivity was discovered, everybody was happy. Wow, instead of liquid helium, we can use liquid nitrogen. That's very good. When fullerenes were discovered, the model met some resistance. Harry Kroto, who died last year, wonderful person, told me that he had 6 papers published against his model. That resistance died very soon. But when quasi-periodic materials were discovered and announced, they met a lot of opposition from the top of the world scientific community, and this will be discussed a little bit later on. So this is the background. In order for everybody to understand my talk, I will start in very simple definition of order, periodicity, and rotational symmetry in crystals. And let's start with a 2-dimensional model like this. And clearly you can see that there is order here. What does it mean, order, for you? It means that if I ask you to continue it in each and every direction, you know exactly how to do that. This is order. You also notice that there is periodicity. The distances between this and this and this and this and so on is equal, so there is order here and periodicity. So there is periodicity in this direction, periodicity in this direction, in this direction. Any direction that you choose, there is periodicity because it is a periodic structure. That's all about periodicity. Now, let's say something about it. Here is a picture. By the way, it's a picture of my hotel in Easter Island. Have you been to Easter Island? Ah, wow. So you see that you see the ocean in the background, and this is also a periodic structure, your 1-dimensional periodic structure, but the motif is not just one atom or particle. The motif is a little bit more complex. So this is the unit cell from here to here. Large, large, small, small, large, large, tiny, small, large, and large. And it goes on and on and on. So the motif can be more complex than just one atom. Okay, that's enough of that. Sometimes you can study very, very complex molecules by arranging them into a crystal. Once you arrange these complex molecules like the ribosome into a crystal, then you can study the position of each and every atom in the structure, usually by using modern synchrotron radiation. It's not an easy job, but it can be done. And the structure of this was discovered by Ada Yonat and his colleagues. She won the Nobel Prize for the discovery of the structure of ribosomes. So you can make a crystal from the ribosomes, and once you have a crystal, you can study the structure of the ribosome. And this is where crystallography is today. It became a magnificent science to study very complex structures, such as biological structures. How about rotational symmetry? Well, here is the same thing with a little handle here. I can rotate it 90 degrees and it looks the same. 180 looks the same. 220, 270 looks the same, 360 looks the same, and because you can do it 4 times and every time it looks the same, it has a 4-fold rotational symmetry. Crystallography. You know, crystallography really started in the ancient times of the Greeks. They invented the term atom. They imagined a tiny little particle that cannot be split. Well, it can be, but they imagined it. And these atoms are arranged in a periodic way so as to create crystals. How did they know that? Because they had crystals with facets, and the angles between the facets were sometimes identical in different minerals. So they imagined that atoms are creating these facets, and they were correct. By the way, if you think that ancient people knew a lot about science, this is not so. They understood very, very little about science. But in this case, they were right. However, up until 1912, there was no way to confirm that crystals are what people thought they were. But in 1912, a German scientist named von Laue created the first X-ray diffraction experiment, and he started the science of modern crystallography by doing that. The Bragg, father and son, came a year later with the Bragg equation, and we had a science. And shortly thereafter, there was a growing group of crystallographers, and the tool of choice was X-ray diffraction. You can see it here. There's a chair. There's one more chair here. One person, come here. Okay. So, we had a science. The tool of choice was X-ray diffraction, and the science was called X-ray crystallography. The group that governs that science is the International Union of Crystallography, and their tool of choice was X-ray diffraction. Not electron diffraction, not neutron diffraction, X-ray diffraction. Why so? Well, because X-ray diffraction developed into a very precise tool to measure crystals, very precise. Electron microscopy was not as precise at the time, it is now, and so is neutron diffraction. Why am I saying that? You'll see later on. So this is crystallography. Now, here is a definition of a crystal before 1991, and the definition is very, very simple. A crystal is a solid composed of atoms arranged in a pattern, periodic in 3 dimensions. Very, very simple. Here is another definition, Arthur Masalski's book. Atoms in the crystals are arranged in a pattern that repeats itself in 3 dimensions throughout the interior of the crystal. Exactly the same, meaning different words. And life was simple. And the science of crystallography was a mature science. A mature science is a science that you believe that you know everything. Yes, you can discover new crystals, but the structures I know. So somebody announces, hey, I discovered a structure which a crystal with a structure DO19, okay, Ta3Al, and everybody said, this is wonderful. Here is the drawer of DO19 structure. We have 1,023 crystals here. Here's number 124, and welcome, and you close the drawer, and everything is fine. It was a mature science. People believed that we understand everything about crystallography. So, this is the background. Crystallography in 1982, here's the book, not Van Vleck, but by Charles Kittel. Many of us studied this book. I marked something in green here. I know you cannot read it because you're far away. And this is why I enlarged it for you. And now you can. So, it says the following. We can make a crystal for molecules, which individually, every molecule can have a 5-fold rotation axis, but we should not expect the lattice to have a 5-fold rotation axis. All right, why so? I will not spend time proving it to you, but there is a simple proof that in periodic crystals, and all crystals were periodic, in periodic crystals you cannot have a 5-fold rotation symmetry, much like trying to tile a floor with pentagon without gaps. It does not work. Okay. So here's an example of atoms in diamond. This is a picture that I took very many years ago. Each atom, each white spot is a carbon atom in diamond, and you see that it is ordered, and you see that there is periodicity here, and there is periodicity in this direction, and in this direction, and in this direction, and in the direction you choose, there is periodicity. It's a periodic structure. The order of carbon atoms in diamond is periodic. The allowed rotation symmetry are the 1, 2, 3, 4, and 6. 5-fold rotation symmetry, as well as any other symmetry beyond 6, is forbidden in periodic structures. It was true. It is true. Okay, no problem up to here. All right. Now, let's go to the reciprocal space. It's the space in which the diffraction pattern occurs. It's a space that we mathematicians have created in order for us to understand diffraction pattern. It's a space in which the diffraction pattern lives. And this is a planar cut through the reciprocal space, and this diffraction pattern is taken by an electron microscope. So what you do in an electron microscope is you make a sample very, very thin, and you have to know how to do that, and you shine an electron beam through the specimen. Electron beam goes through, and on its way, it also diffracts sideways. So this is a transmitted beam, and many diffracted beams all around it. So here we have, this is the transmitted beam, and all the beam around it were diffracted from that crystal. And you have to put the crystal in a certain orientation, so it will diffract and give you a very nice diffraction pattern, such as here. Now, this was taken from a periodic crystal. And when you take a diffraction pattern from a periodic crystal, the diffraction pattern itself is also periodic. And you see that it is a periodic pattern, and there is periodicity in this direction, and periodicity in this direction, and periodicity in every direction that you choose. There is periodicity. And the periodicity of diffraction pattern peaks in the reciprocal space. The rotation symmetries allowed are, again, 1, 2, 3, 4, and 6. No 5 rotation symmetry, and nothing beyond 6-fold. It can happen, and the science was happy and mature. And now came a new definition of a crystal. And this new definition was made by the International Union of Crystallography. And I must tell you that the people that occupy those positions, the high position in the International Union of Crystallography, are hardcore mathematical crystallographers. These are no-nonsense people. I mean, you have to define everything from the foundation. Every word that you say must be very accurate. And they came up with this new definition of a crystal, which sounds like a poem. I'll read it to you slowly. You will see. It's a poem. Now, this poem was composed by the hardcore mathematical crystallographers of the International Union of Crystallography. What happened? Let's read it slowly. It doesn't say a crystal is. We are humble now. By crystal we mean. By crystal we mean any solid having an essentially, not precisely, essentially discrete diffraction diagram. And by aperiodic crystal we mean any crystal in which 3-dimensional lattice periodicity can be considered to be absent. Is this a soft definition or what? This is a crystal nowadays. And the crystal is not defined by the position of the atoms anymore. It is defined by the reciprocal space. A crystal is defined by the diffraction pattern. Something happened. What happened that we need this dramatic change, this shift of paradigm, this paradigm shift in crystallography? And what happened was, in 1982, that was the 70th birth of crystallography. Remember 1912, von Laue, 1972, 70 years. And This was the year quasi-periodic crystals were discovered, and this is the subject of my talk. So now we can start. Let me take you back to my logbook. Lesson number 1 to the students among you. Whatever you do in the laboratory or on your computer, make a logbook. Write it down. You will remember your experiment next week, yes you will, but you will not remember it next year. And that may be very important. So here is my logbook. It was not meant to be seen by anybody. This is like private writing for myself. This is now why it looks not very ordered, but it has a lot of information. So let's see what it has. It has the date, April 8, 1982. All right, that's important. It has the composition of the alloy that I was studying, aluminum 25% manganese. Right? And it was rapidly solidified. It doesn't say so because all the alloys that I was studying were rapidly solidified. And this is the plate number in the microscope. Those days, we took pictures on glass plates. And then we took them in the box, in the dark, to a place where we did all the chemistry to make these plates sources of pictures, and then we could print them. Nowadays, it sounds crazy, right? I know, yes. So this is plate number 1720. There were many before and many after. This is book 1 of 5 books, by the way. All right. And SAD, selected area diffraction. Selected area diffraction. This is the afternoon of the day. I know because the previous page, you can see the shadow here. Previous page was a totally different material, and this was the morning. So this is the afternoon of this date, like 2 o'clock after lunch, and I'm happy now. And so I took these pictures, and then I arrived at picture number 1724. 36 came in magnification. It's a picture with a magnification 36,000 times. And I look at this picture, and I say, wow, that's interesting. Now I will show you what was interesting in that picture. And then I said, how does the diffraction pattern look like? So immediately I take a diffraction pattern, which is the next picture, 1725. I will show you these two. And I wrote here, tenfold rotational symmetry with 3 question marks. That's forbidden. How can it happen? So I spent the rest of that afternoon trying to understand what was going on. Let me tell you what was on my mind. I thought that I have a structure of twins, a twinned structure. From my past experience, I found such twin structures with the very same diffraction symmetry. So I said, okay, these are twins. I spent the rest of that afternoon until the evening trying to find the twins, and I could not find them. There were no twins there. I knew from the afternoon of this date, April 8, 1982, that the structure I have has no twins. What was it? I didn't know. But twins, it was not. Why am I emphasizing it? Because later on, opponents of quasi-periodicity claim, oh, these are twinned in periodic structures, and they were all theoreticians, of course, and they never saw an electron microscope, and I was an expert in electron microscopy, and we will discuss it later on. So, this is it. The Nobel Committee said that it's very rare that you can trace a discovery to a date and an hour. All right. So, this was the picture, 1724, in which that I said, what's going on? So what's different about it? Okay, this is a single crystal. It's a small crystal. This is half a micron, right? So the crystal is about half a micron to a micron in size, and there are many of them. It's a polycrystalline material, okay? So what's strange about it? Well, what's strange about it is that some of the crystals are pitch black, like this, and this, and this, and this. And this is a bright field image using the center beam to take the pictures for those electron microscopists among you. when you see a dark crystal like this, it means that it diffracts heavily. It diffracts so heavily that there is almost no intensity in the transmitted beam. And I have never seen in my life such a black crystal. So I say, how does the diffraction pattern look like? So I take a diffraction pattern from here, just from this single crystal, and this is what I see. I look at the diffraction pattern. I tell you exactly what happened during that minute when I observed it. I said, wow, that looks very different. What is the rotational symmetry? So I start to count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. No. Impossible. 1, 2, 3. And then I write in my logbook 10-fold with 3 question marks. Turns out it's 5-fold. But in order to do that, I had to take something which is called Kikuchi pattern, and I will not show you that one. So on the first observation, it was 10-fold. Later on, it was clear that it is 5-fold. So what's strange about it is not only that it has a 10-fold rotation symmetry, it has no periodicity. Right? You take the distance from here to here, you multiply by 2, you get here, and there is nothing there. No periodicity, 10-fold rotation symmetry, very, very strange. Electron diffraction from the icosahedral phase has 5-fold rotation axis, and it is not periodic. So you can see here that there is no periodicity, and the ratios involved, this distance divided by this, brings you to Fibonacci number. Of course, you cannot do it by measuring. You cannot, by measuring, arrive in an irrational number. Just if you take 2 quantities that divide by each other, it will always be a rational number, and this is an irrational number. But closed, you can get there. So this is a Fibonacci number, and I will tell you about Mr. Fibonacci, blockhead of Pisa, in a few minutes, because he is such an important mathematician that we have to learn about it. This is general knowledge. Okay. So this is it, and this is the Fibonacci number, also known as the golden mean. All right? It's 1 plus root 5 divided by 2, 1 plus 6, 1, 8, an endless number of digits, because it's an irrational number. Okay, why is it called the golden mean, by the way? People that claim that they understand in aesthetics never argue with people who claim that they understand aesthetics. You will never win. They claim that it has a pleasing ratio, very pleasing to the eye. Why not 1.6, but must be Fibonacci number? Because people of aesthetics claim so. Okay, so if you take the distance from the nose to the belly button divided by, then you arrive, if you are so beautiful and perfect, then you have this ratio. Fibonacci number figure, right? All right. So, but this diffraction pattern was not the only one. This is the 5-fold. In an electron microscope, you can tilt your specimen, and you can rotate your specimen to different positions, okay, in a goniometer. And this was a 5-fold, 2-fold, 5 again in this direction, and 5, 3, 2, 3 in this direction. And this set of diffraction pattern has an icosahedral symmetry. I will talk about it in a moment. I'll tell you what an icosahedron is. And this is why we call it the icosahedral phase. The first name of the first quasi-periodic material was named the icosahedral phase because it has icosahedral symmetry. Okay, so to make a long story short, everything happened on that day in 1982. I was at NIST for a sabbatical when I made the discovery, and in the year from the end of 1981 to the end of 1983, I was there. I went back to the Technion. I still didn't know what I have, but I knew what I didn't have. At the Technion, I met the first person who was willing to work with me. His name is Ilan Blech. He left the Technion shortly thereafter, and now he's in California. And we sat together and wrote a paper. He developed a model that could explain the phenomenon that created these structures. The model was based on joining icosahedra in space in such a way, arbitrary way seems to be. okay, entropy controlled, as we have an expert here. And once they join, they create these structures. We wrote a paper together, and now it is the summer of 1984. I came back to NIST, and National Institute of Standard Technology. I was there every summer for 3 months, every summer. So I came back a year after my sabbatical with a paper in my hand. Those days, when you send a paper for publication, you print it. In fact, those days, very few scientists could type. We had typing machines, you know. We had secretaries that typed for us. They typed my paper, I corrected it, they typed my paper again, I corrected it again, they typed it again, and finally it was good, and the last correction was with a pen, that's okay. I sent it to Journal of Applied Physics, and a few weeks later, the paper came back, also in an envelope, stamp, my address was on it, with a letter. And the letter said, "Dear Dr. Shechtman, thank you so much for your contribution. We have decided not to send the paper for review because we think that it will not interest the community of physicists." Okay, so I took that paper and sent to a metallurgical journal called Metallurgical Transactions. They accepted it and they published it. But they published it more than half a year deep into 1985. Meantime, I was there at NIST. At that time, it was called NBS, National Bureau of Standards. I showed that paper to my host, John Kahn, who invited me there. And I asked him, why do you think it was rejected? John Kahn came with the idea that we should do something completely different, publish a short publication without the Lamblèche model and send it to a fast publication journal such as PRL, and this is what we did. He also invited a mathematical crystallographer from France. His name is Denis Gratias, and the three of us sat together and composed a paper. John Kahn knew how to put the right words. Denis Gratias added the language of mathematical crystallography, and we sent a paper for PRL, and it was accepted and published very, very quickly. So the second paper was published long before the first paper. So this is paper number 1, Shechtman and Blech, and we should skip this. So this is paper number 2, Shechtman, Blech, Gratias, and John Kahn. It's only a 2-page paper. This was the first announcement that was published. And when this paper was published, hell broke loose. I started to receive emails, telephones, telegrams from all over the world. "Danny, we have it, this is fantastic." I explained what I did. People repeated my experiments, and within 1 week, huge community could repeat my experiment. They received the very same results, not surprisingly. And from that date on, a growing community of avant-garde, young, active scientists grew all over the scientific world, in the United States, but mainly in Europe and in the Far East. And this young community continues to be very active till today. And they took my discovery and turned it into a fantastic, fast-growing science of quasi-periodic material. And you have Sharon here and other people that do research on this subject very successfully. So this was the second paper. It was published on November 12, 1984. Okay, so now let's go to the basic. What is an icosahedral symmetry? This is an icosahedron. It's a Platonic structure. And many of quasi-periodic crystals have icosahedral symmetry, not all of them. There are quite a few other structures of quasi-periodic material. And this icosahedron has 6 5-fold axes. What does it mean? It means that if you put your eye here, exactly here, look down to the center, don't get too close. And then you see that there is 5-fold rotation symmetry here, and there is 5-fold here, and here, and here, and here. 6 of them. Right? This is just negative of that, so you don't count it. 10 threefold, so the way you look at it, you see threefold rotation symmetry, and 15 two-fold axis. This is the icosahedron, and the angles between the fivefold, the two fivefold, are exactly the angles between the two fivefold in the diffraction pattern, and so on. And this is I would call it the icosahedral phase. Okay, so in other ways, let me show you another way to understand icosahedron, and let's look at a soccer ball. So this is a soccer ball. You have a soccer team here? Okay, are they any good? Yeah, people do. Well, maybe. Let me promise you one thing. If you talk to your team of soccer ball players, you will discover something shocking. They do not know that they play with icosahedral symmetry. Okay. A football is made of patches, 6-fold and 5-fold, and this is the way it looks. You look from here, it's clearly 5-fold rotation symmetry. From this position, 3-fold, 2-fold, wonderful. Okay, now let's talk about quasi-periodicity. What is quasi-periodicity? And to understand quasi-periodicity, we have to go into the fundamental aspects, and the man in charge, Leonardo Fibonacci de Pisa. Pisa, you know, in Italy, where the inclined tower is. Anybody been to Pisa? 1, 2, 3, 4. Okay. I see the older guys have been there. The younger guys will be there. Just by the way, for those of you who've been there, just behind the inclined tower of Pisa, by the way, all towers in Pisa are inclined, because I will not go to the reason why. But just behind it, 50 yards behind it, there's a graveyard under a roof. And in that graveyard, there's a statue to honor Leonardo Fibonacci de Pisa. And I will show you that statue soon. So this is a picture of Leonardo Fibonacci de Pisa. And this is the statue. This is a real picture of the statue that is standing just behind the inclined tower of Pisa. He was the greatest mathematician of the Middle Ages and for many years after that. So what is his contribution to quasi-periodicity? To understand his contribution, we have to go to his rabbit experiment. Okay, it's a Gedanken experiment. You think about it, okay? You don't have to raise rabbits to do the experiment. So he said the following. Let's assume that there is one female rabbit in the first month. And she has a husband or a boyfriend, and he comes for a visit, and in the next month she has a baby rabbit, right? So every month, this happens every month. So every month she has another baby rabbit. And the baby rabbit has to mature 1 month before it can reproduce. So these are the rules, right? Every month a baby, and it takes a baby to mature for 1 month before it can reproduce. Now you know the rule. It means that there is order. You can continue this list. So in the 3rd month, this mother gives birth to a little one, this one matures. In the 4th month, this mother, this one, gives birth to a little one, this one matures, and this one gives birth to a little one. So now that you know the rule, you can continue this forever. I stopped here because this was the end of the page. Okay, so why is this so interesting? Well, first of all, we have large, small, large, small, large, small, large, small, large, small. There is no motif of any size that repeats itself periodically. None. But it's an ordered structure. So ordered that each one of you can continue this list forever. So this is the quasi-periodicity in one dimension. Okay. But now that we are here, let's say a few more words about the Fibonacci series. This is the number of rabbits in each month. 1, 2, 3, 5, 8, 13, 21, and so on. 1 plus 2 is 3. 2 plus 3 is 5. 3 plus 5 is 8. And this is this equation, right? an equals an minus 1 plus an minus 2. 5 is 2 plus 3. This is what this says. What this equation says, and this is the Fibonacci number, this is how we get to it. If you continue this list forever, to infinity, and you take the two last number of rabbits, divide them by each other, then that ratio an divided by an minus 1 in infinity, you get the Fibonacci number tau, which is this. He published it in the book Liber Abaci, Book of Abacus, or Book of Mathematics. A word about this book. This book was not designed to tell us about quasi-periodicity. It was designed for another purpose. Leonardo Fibonacci di Pisa tried to convince the merchants of Pisa not to use Roman numerals to make calculations. It is impossible. Use the Indo numerals that Arab merchants brought to Europe, and look how wonderful mathematics can be, how easy it is to do, and this is what the book is about. But there's a chapter there, and that chapter brought us to quasi-periodicity. Okay, enough of that. How about quasi-periodicity in 2 dimensions? Roger Penrose. Roger Penrose is an eminent British scientist living in our times. He is a physicist, philosopher, amazing scientist. And he came up with Penrose tiles. Penrose tiles are 2 tiles that if you put them together according to certain matching rules, you have to know how to do that. And this is why I marked it with arrows. You have to put one arrow with touching another arrow in the same direction. Once you do that, you arrive at a Penrose tile, and this Penrose tile can cover a 2-dimensional surface with no 2-dimensional area with no gaps. And when you take a diffraction pattern from this, you will arrive at something that looks exactly like what I discovered in quasi-periodic crystals. And this is work that another scientist did. His name is Alan Mackay. Alan Mackay is also a British scientist, British crystallographer, living in our time. He celebrated 90 years old a few days ago. He's an old guy, he's a shrewd guy, he's a wonderful scientist, and he has a sick sense of humor. I like him. So he took Penrose tiles and put a dot in the center of each tile and gave it to his friend who had a laser. Those time lasers were things like that, not like that. And he said, make me an optical diffraction pattern of that. He did, and lo and behold, 5-fold rotation symmetry diffraction pattern, sharp points in the reciprocal space. So this is the connection. Okay. So this was in 2 dimensions. How about 3 dimensions? Well, 3 dimensions are quasi-periodic crystals, such as this one taken by one of my students, and that was that. Enough of science, now stories. When I started to talk about 5-fold rotation symmetry in crystals, people said to me, what do they teach you at the Technion? Don't you know it is impossible? I said, yes, I know. Let me give you an example. My group leader, not John Kahn, John Kahn invited me. My group leader came to my office one day, smiling sheepishly, putting a book on my desk called X-ray Crystallography. And he said, Dr. Shechtman, please read this book, and you know that what you're talking about cannot be. And I said to him, you know, I know this book. I don't have to read it. I teach at the Technion. I know this book. I'm telling you, my crystal is not in the book. Took the book back, came back a few days later, and he says, Dr. Shechtman, you are a disgrace to my group. I cannot have my name associated with your name. Please leave my group. So I left. Silence. It was not so terrible, because all it meant was that I had to find another group leader that would adopt the scientific orphan. I found one. He adopted me to his group, and everything was fine. I didn't have to leave my office or my laboratory. Everything was the same, but instead of reporting to this secretary, I reported to that secretary. Life went on. Okay. So this started the years of rejection. Some people supported, John Kahn among the most powerful support, but many others. And I told you there's a growing group of young scientists, and the group was growing fast, but the opponents were by far a larger number of them. And in the first period, I felt very uncomfortable because of all this rejection. And if you want to imagine how I felt, it was something like that, and it is between the years before I published the publication, and it's something like that. It was heavy. It was heavy and sort of not easy walking. Then I published 1984 until 1987. By now, there was a growing group of supporters, but the major opponent was the International Union of Crystallography. They said, everything is nice and dandy, but we don't believe in that electron microscopy. That's not the tool of choice. You bring us X-ray diffraction patterns, then we can talk. We did not have stable quasi-periodic crystals at that time that we could grow to create X-ray diffraction pattern. Nowadays, we have microbeams that can do it on small crystals, but those days we didn't. So we needed crystals, real crystals that you can hold in your hand. Can be millimeter or smaller, but not a micron. But colleagues mainly in Japan, my friend, okay, in a minute, Anpeng Tsai, at that time he was in Tsukuba, discovered few stable quasi-periodic crystals. He grew them. He created a diffraction pattern. Also, friends in France did the same. And he sent me the diffraction pattern that looked like this. This is X-ray diffraction pattern, our pattern. Beautiful hour pattern. 5-fold rotation symmetry, 3-fold, 2-fold. The year was 1987 by now. This is 3 years after publication. And I went to Australia to participate in the meeting of the International Union of Crystallography in Perth, Australia. Perth is on the west side of Australia. And I presented a talk. And when I showed this picture, people said, okay, Danny, now you're talking. Now we have an X-ray diffraction pattern. Yes, now we have something to work with. The International Union of Crystallography created a group that created a new definition for a crystal, and that new definition I showed you in the beginning of my talk. So this was the end of this, and now you think, okay, hey, the International Union of Crystallography agrees, who will object? Not so fast, because then there was Professor Linus Pauling. Now, Professor Linus Pauling was undoubtedly the greatest chemist in the United States of the 20th century. There's no question about it. He wrote the books, he wrote the paper, he explained, he taught. He was an amazing scientist, really. He was the godfather of the American Chemical Society. He was the head of the American Chemical Society. Fantastic. The only difference between Linus Pauling and God is that God doesn't think that he's Linus Pauling. He thought he understood everything better than anybody else. Okay? He didn't. Nobody does understand everything better than anybody. Nobody. We are human beings. He objected quasi-periodicity vehemently, and he was a flamboyant speaker. Oh, yes. He stood on stages fighting quasi-periodicity and coming up with models. First, he said that quasi-periodic materials are twins in periodic crystals. I knew from day one they were not. I knew it. I was an electron microscopist. I was a very experienced electron microscopist. I was not. And then he said, okay, let's build structures that if you diffract from this structure, you'll have the same diffraction pattern. So he came up with a model. He was hiding it under something like this. And wow, here is the model. You diffract this model, that's what you get. In 1 week, somebody from India or then said, no, Professor Pauling, you are mistaken. It's close, but it's not quasi-periodic. He said, okay, no problem. Here's a larger model, and a larger model, and a larger model. Let me tell you something. So you understand his basic mistake. He tried to reach irrational numbers by taking two numbers and dividing by each other. This is what he did. And it will never work. It becomes closer and closer and closer. Let's say that somebody says, okay, the ratio of a circumference of a circle divided by the diameter is a rational number. Oh, really? How can you prove it? He said, well, here I draw a circle, and I draw the diameter, I measure the circumference, I divide by this, voila, rational number. He said, well, yes, nice, it's close to pi, but it's not really pi. He says, no problem, here's a larger one, and a larger one. You can get closer and closer to pi, but you can never reach pi by dividing two numbers. And this is what he was doing. It was a fundamental mistake. Okay, so the fight continued from 1984 to 1984. Then it was over because Linus Pauling died. Now, that's not funny when people die. I'll have to explain it to you one day. Okay, so you understand his basic mistake. I met Linus Pauling twice. Once in a conference, we had dinner together, and 100 people looked to see the fish. There were no fish. We were very polite to each other. We agreed about vitamin C. We agreed about everything in science except quasi-periodic material. And then later on, I came to visit his home in Palo Alto, California. He had there the Linus Pauling Research Institute, which was really a nice place with all the books that were translated to all these languages. It was a shrine for Linus Pauling. And I gave a talk to one person. This was the smallest audience I ever had. One person. 1 hour talk. There were slides there. Anybody knows about slides? Yeah, okay. Slides in a cassette. If they fall down, bad news. Anyway, so I gave a talk. He was listening for 1 hour very carefully. And then at the end of it, he said, okay, Dr. Shechtman, I don't know how you do that. I said to him, you know, Professor Pauling, if you ever agree with me, don't keep it a secret. And he said, yeah. We had a lot of correspondence between us. He and his followers kept that correspondence, and you can read the correspondence. It's somewhere on the internet. So that was the end of that. All right. Now, I want to mention a few names that made seminal contribution. You know about Roger Penrose, you know about Ellen MacKay. They are the tiling people, okay? And Ellen MacKay did the reciprocal space of the Penrose tile. Ilan Blech, Denis Gracias, and John Kahn wrote the papers with me. Ilan Blech was the first. Dov Levine, Paul Steinhardt. Dov Levine was a student of Paul Steinhardt. And they came up with a mathematical model based on Roger Penrose tiles, three-dimensional tiles, that could explain the diffraction pattern and everything else. Ilan Blech model was a physical model of Orcosahedra joining in space, and their model was a mathematical, idealistic model. Okay, so whereas before order was synonym to periodicity, now we know that order can be either periodic and it can be quasi-periodic. And quasi-periodicity, as Sharon may want to tell you, is a fundamental phenomenon in nature. It's not just a few quasi-periodic materials that appear here and there. So now I want to let you ask questions, but I will ask the first question, and I will also answer that question, okay? And then you can ask questions. My question is very obvious. Why is it that quasi-periodic materials were not discovered before 1982? 70 years of crystallography, thousands of eminent crystallographers around the world didn't find quasi-periodic material. Why? Why is it me they did find it. I will give you the questions and then the answer. Is it because they're very rare? So there are only very few, and I had the chance to stumble upon one of them? Or maybe they're not stable, you touch them, they disintegrate, so people could not have a chance to study them. Or are they difficult to make? And I, with my magic fingers, made one. Or are they made of rare elements? Praseodymium, gadolinium, and a touch of zinc? What is it? What is the reason that there were no discoveries for so long? So, are they rare? No. Quasi-periodic material are not rare. There are hundreds of them. Here is a small partial list based on aluminum. So you find them in aluminum, cobalt, aluminum, chromium, aluminum, iron, aluminum, long list. There are hundreds of them. They're not rare. Somebody could have stumbled upon one of them, but nobody did. Okay. Are they not stable? Many are not stable and transform to periodic structure at high temperatures. But QCs, quasi-periodic material, QCs, right, can be thermodynamic stable. And here are a few examples, and these are not all of the examples. Most of them, by the way, were discovered by Ankpen Tsai. He is now in Tohoku University in Sendai, Japan, but others were discovered by other people. And so many of them are also stable thermodynamically. So somebody could have done it. Are they difficult to make? Not at all. They're very, very easy to make. You can make them by casting, by rapid solidification, by single crystal growth, by electrodeposition, by CVD, by PVD. Any technology to manufacture metallic alloys can be used to make quasi-periodic crystals. It is very easy to do. Nothing to it. Fact is that when I published the paper, a few days later, people came up and said, we have it, we have it. Very easy to do. So this is another reason that were not discovered before. Are they made of rare elements? No, not at all. They're made of iron and aluminum and chromium and copper and titanium, and millions of tons of these elements are used every year. It's very common, not rare elements at all. So why is it that quasi-periodic crystals were never discovered before 1982? This was the question. Now I will give you the answer, my answer. Now it becomes subjective. Right? Up to now, everything was fact. Now it's subjective. Number one, transmission electron microscopy. Quasi-periodic materials had to be discovered by transmission electron microscopy because they were very small. Once you made them, the crystals were very small. If you took a diffraction patterns, as I did also, from a material that you prepared, you will get rings. Because a tiny little crystal, you get rings in the diffraction. And if you have rings, you do not know anything about the rotational symmetry. And the rotational symmetry was key to understanding the structure. So it has to be done by TEM. So I look at your eyes and you say, okay, big deal, TEM. You know how many thousands of people are working on TEM around the world? Why you? Because driving the TEM is not enough to do good science on a TEM. And most of the scientists around the world, including many of you, who do electron microscopy, maybe know how to manipulate the joystick or whatever you use here, but they do not know electron microscopy. Learning how to do contrast analysis in electron microscope, you have to dedicate yourself to electron microscopy. You have to know the theory to the extent that you can teach a class in electron microscopy, and I taught many classes in electron microscopy, and you have to know contrast analysis very, very well. And then you are an electron microscopist. And you know, I can tell you that in my department of material science, we are pioneers in electron microscopy in Israel. And over the years, we had hundreds of students who used our electron microscope, hundreds of them. You know how many electron microscopists we have produced? Maybe 15 in 40 years. One every 3 years. And they are doing electron microscopy around the world and in different laboratories in Israel. Very few become expert in electron microscopy. You have to be an expert in electron microscopy to make a discovery. You have to know what is possible. You have to be you have to have the strength to check yourself several times before you start talking. But when you talk, you know that you're right. Right? When Linus Pauling was against Danny Shechtman, he was the most eminent chemist in the world, maybe, but I was an expert in electron microscopy and he was not. And that was that. Okay. TM, you have to be a professional, as I just mentioned. Professional electron microscopy. Very few of them exist in the world. You have to have tenacity. Hey, when people around you say, Danny, I mean, you know, this cannot happen. What do they teach you at the Technion? You may lose interest by saying, okay, guys, this is too complicated and I have my career, You have to have tenacity. Here is lesson number 2 to the young people among you. When you see something different in your studies, something that doesn't look right, don't let it go. Be like a Rottweiler dog. You bite, you don't let go. Until you find out what it is. In most cases, it will be an artifact. In many cases, somebody else discovered it 45 years ago. But in some cases, just in some cases, you have made a discovery which will create your future. So don't let go. Let me give an example of somebody, a bright scientist, young at the time, not anymore, whom I know from Europe. He saw my material before me, years before me. He saw the same diffraction pattern, everything, while doing his PhD. He's about 5 years older than I. How do I know it? Because his professor told me that. And later on I met him. Professor says, you know, the one day I go through the slides, remember glass plates that my students did? I pull one, your diffraction pattern. I look at the date, years before you. Done by this student. I call my student. Hello, student. How are you doing? Thank you, professor. I'm fine. How are you? Said the professor, do you know that you saw Danny Shechtman diffraction pattern before him? Said the ex-student, of course, professor. Of course I know. Said the professor, why didn't you tell me? Said the student, you know, professor, if I told you, you would want me to stay for 2 more years on my PhD? Be like a Rottweiler dog. You find something, you don't let go. This is your future, maybe. All right? Okay. Tenacity. Believing in yourself. This is called self-efficacy for the psychologist among you. Believing in yourself means saying to yourself, I am a professional in something. And this is my message number 3 to you, young people. If you want to succeed in science and continue to be scientists, find something that you like and try to become number 1 in that. Right? And it is easy to do nowadays because information is available everywhere. You can talk to professors freely. Okay? It's not the old system. You can knock on the door, talk to a professor, find the information you want, become expert in something. And I promise you, if you have broad knowledge of science, you have to know something about material science, about biology, you have to know enough mathematics, you have to know about thermodynamics, you have to know about everything. But develop one peak of expertise. And if you have these 2, I promise you, you'll have a wonderful career in science. Believing in yourself. And number 5 and last, resilience. I can tell you that my promotions were delayed. The chair of my department hated me. Why would anybody hate me? But he did. When I was up for promotion, he went to visit Linus Pauling for the sole purpose so that Linus Pauling will object my promotion. And he wrote to the president of the Technion, how can you promote a person that Linus Pauling, the sun in the sky, is rejecting his science. How can you promote a person like this? Aha. If the Technion has doubts, they promoted me right away after this letter because they knew that professor. Okay, so this is resilience. To finalize, here is a nice picture taken by Anpeng Tsai, my colleague. And these are quasi-periodic crystals of the aluminum manganese system. And look here, you can see 5-fold rotation symmetry and 5 again. And you see 3-fold, okay? And you see 2-fold. Beautiful. And he painted it artificially. This is scanning microscopy. He painted it artificially, the rose to look like the cherry blossom in Japan, okay, that they admire so much. Okay, thank you very much.
The new coating is made of common synthetic rubbers like polyurethane. It's more durable and less expensive than earlier ice repellent coatings, and ice slides off with only the force of gravity or a light breeze.
To our knowledge, we've not found any other coating that can survive these kinds of challenges.